we are going to explain how we can use this sample mean and the sample variance to make statistical conclusions about the parent population mean. Okay, and we are going to give you a summary about these theoretical proofs. The first summary is this: if we have a parent population following any arbitrary distribution, so we have a parent population, but we do not know its distribution. It can be any type of distribution, not necessarily normal. However, let's just say, just like in all distributions, there is a theoretical mean and a theoretical variance, which are unknown. So for the parent population, the mean and the variance are unknown, we say. And what do we do for that? So if I want to make comment about the parent population behavior, what I can do is to draw a sufficiently large sample size of n from the population. Okay. So I basically draw a sufficiently large sample size, but the sample should be a random sample. Okay, random sample. It is important. If it is not random, then we cannot apply central limit theorem. The sample mean x bar is going to be the best choice for me to estimate the unknown parent population mean mu. Okay, so if I cannot know the unknown mean mu, I can choose a sample, random sample, and take its mean. And this mean, sample mean, is going to be my best choice to estimate the unknown parent population or predict the unknown parent population mean mu. Okay, and similarly, the sample variance is going to be my best choice to estimate the unknown parent population variance sigma square. Okay, so these are just going to be predictions. These two values are going to be predictions for respectively the unknown parent population mean and unknown parent population variance. Okay, the more the sample size you use, the larger the sample size, better the accuracy of these estimates. Okay, now we are going to practice this in this small type of question. In a production lot of batteries, 8 batteries are randomly selected and exposed to a lifetime test, it says. Okay, 8 batteries are randomly selected and exposed to a lifetime test. The following are the observed durabilities of these batteries in hourly time units. Okay, so we have used 8 batteries in the lifetime test, and the duration of the batteries are observed to be equal to 11.39 hours, 8.92 hours. So these are decimals, my friends. So these are not just minutes, okay? 8.92 means 8 hours and 0.92 hours, okay? So these are given in hours, hourly units. As you can see in these 8 batteries, the largest of the observations is 11.39. The smallest of the observations is 8.40, I guess. Okay. And it says, make a guess for the mean lifetime of the batteries in this production line. So actually, my friends, in this production lot, maybe we have manufactured thousands of batteries. Let's just say we have manufactured 100,000 batteries. Okay, we are going to sell this 100,000 of batteries. Now, if we want to make a guarantee for the duration of these batteries, we need to give a solid information to the customers about it. Okay, on the average, how many hours does this battery work? Okay, we need to give a solid answer. But if you really want to give the true answer, the truest answer, the correct answer, you need to perform a lifetime test on all of the batteries that you manufacture. But once you test all of the batteries, everything will die out and you are not going to sell them. Okay, so that's basically logical, right? So we cannot apply quality checks, quality control checks, okay, on all products that we manufacture. Because of that reason, even though we manufacture thousands of batteries, we randomly select a few of them, which is 8 here. We randomly select 8 batteries, okay? And by using these 8 batteries, we create a sample of observations on the durabilities of these batteries, okay? It says, make a guess for the mean lifetime of the batteries in this production lot. So it says, make a guess about the true average of the batteries. So what can we do? We can basically take the average of the sample observations, the sample mean, and the sample mean would be an accurate, unbiased estimate for the parent population mean. In part B, it says make a guess for the variance of the lifetime of the batteries in this production lot. So again, the sample variance is going to be an unbiased estimator for the parent population variance. And finally, the last one, what should we do to get better guesses of the mean and the variance of the lifetime of the batteries in this production lot? There may be many suggestions to answer C, but the first thing that we know is to increase the sample size. Okay, right. So the answer of C is already known. I mean, if we are talking about 1,000 batteries or thousands of batteries, running a quality test only on 8 batteries is not going to give us accurate, correct results. Okay, they are just going to be guesses, but bad guesses, not good guesses. If you want to increase the accuracy of these guesses, you definitely need to increase the sample size. Okay, let's just stick to our sample. Okay, we have n equal to 8, or sample is of size 8. And we want to make guesses on the true parent population mean and the true parent population variance. And the distribution is not known. However, we can say that the sample mean of these 8 observations, which is 9.9725, is going to be a good guess. Not a good guess, but is the best guess that we have with our sample for the true parent population mean. And the sample variance coming from 8 observations is going to be evaluated by dividing the squared deviations to 7. Be careful, n-1, we are dividing it to 7. Therefore, 0.987 is going to be the variance estimate for the sigma square. Okay. Now, if you want to get accurate estimates predictions, we can increase our sample size as long as it is affordable. But when it is not affordable, okay, when the cost is going to exceed the benefit coming from that information, then do not do that. Okay, so that's the golden rule. Statistics is beneficial if the information generated is beneficial. If the information that is generated is not beneficial, then statistics is just cost. Okay, it costs us. Now, here's the thing. So we have said that if we want to make a guess about the true mean of the parent population, then the sample average is the best guess that we have. If we want to make a guess about the variance of the parent population, true variance of the parent population, then the sample variance is the best guess that we have. However, when you are calculating the sample variance, you calculate the squared deviations by subtracting the sample mean from every observation. Therefore, you divide this summation, sum of squared deviation, to n-1. Because when you do it like this expectation of s squared becomes exactly equal to the true parent population variance. Okay, it yields an unbiased estimate when you divide it to n-1, when you divide the sum of squared deviations to n-1. However, here's the thing. Let's just say we have a simple random sample of size n coming from the parent population. The distribution of the parent population is not known again. It is unknown. However, the mean is known. The mean is known. However, the variance is unknown. Okay, the mean is known, the variance is unknown. Okay, let's just say we have products, and in these products we use a certain type of chemical. Okay, so we have manufactured 1,000 products, let's just say, and we are using a certain type of chemical. Now, the chemical is homogeneously distributed in all of the products. However, by some different conditions in production, okay, in every product that we manufacture, the chemical percentage in that product can be different, okay? For example, I mean, when you purchase a product in supermarket, let's just say biscuits, okay, you are purchasing biscuits, the amount of sugar in each biscuit is different. I mean, though it is the same brand, because of the conditions, undesired conditions in the production, we cannot be exactly say that the percentage of sugar is always the same in every product. Okay, so there is a deviation. It's a small deviation considerably. There's a standard because, but we cannot say that every product has the same type of chemical percentage. Okay. However, what we know is this: in a production lot, we know the exact amount of chemical that we use. So we do not know at each product if we are going to have the same percentage of the chemical, but because we know the total amount of chemical that we use, we can easily say that by dividing the total amount to the number of products that we manufacture, we can calculate the average amount in each product. So there can be conditions like we do not know the distribution of the parent population, but we know its mean, theoretical mean, because it is supposed to be equal to mu, because we know the total amount of product that we use. However, the variance is unknown. Okay, so there may be conditions like this. The parent population distribution may be unknown, the variance may be unknown, but the mean can be known. In that case, if we want to make a prediction about the unknown variance sigma square, in that case, we are going to estimate it with sample variance. However, this time the sample variance is going to use mu instead of x bar. So when it is going to calculate the sum of squared deviations, the deviations are calculated with respect to the true parent population mean, because it is known. Why should I use a lie? The sample mean. Why should I use a lie? Because if I know the parent population mean. Because of that reason, we can calculate the sum of squared deviations by using the true parent population mean. However, this time you do not divide it to n minus 1. This time you should divide it to n, because you are not telling a lie anymore. Okay? You are not going to be punished. You do not have any degrees of freedom reduction. Okay, so you can freely choose your random sample if you resample again, because you always know the true parent population mean. This time, the sample variance will be calculated by dividing to n, and this time it is going to be unbiased again if you divide it to n. Okay, so the correct choice for the denominator this time is going to be n. So we can show it by taking the expectation of the mean squared deviation. Okay, so this is the sum of squared deviations. By dividing it to n, we get the mean squared deviation, and the expectation here calculates the expected value of s square. And again, we can do the same operations one by one, and in the end, you are not going to see any term related to sigma square over n. And once everything cancels out, so I'm not going to explain the details of this equation, you should be able to understand anymore. So in the end, you are going to see again the expected value of s square if you know the parent population mean mu, and if you divide this sum of squared deviations to n, again it is going to be unbiased. So what is the result here? Okay, if we have a parent population following any arbitrary distribution with known mean but unknown variance, okay, if you know the mean, again, what you can do to predict the variance is to draw a sufficiently large sample size, random sample size from the parent population. The population mean is known, the true mean mu is known, therefore the sample mean would not mean anything anymore, okay? I mean, you can calculate it, but it's not going to help with anything because you know the true parent population mean, you know the true value. However, the sample variance is unknown. What you can do is you can predict it with the sample variance formula. You can predict the true variance of the parent population with the sample variance. However, in the sample variance, be careful. You need to use the true parent population mean instead of x bar now, and you are not supposed to divide the sum of squared deviations to n minus 1 anymore. You need to divide it to n, and this is going to be the best choice to predict the parent population variance. Okay. And in this 8th question, again, we have the same observations. Let's just say the engineer who designs the batteries says that the batteries are designed to exhaust in 10 hours. So we say that according to the engineer, he says that the design of these batteries gives a true expected lifetime of 10 hours. So the parent population mean is known here. Okay, 10 hours gives us true parent population mean. In that case, what would be an estimate for the variance of the lifetime of the batteries in this production lot, it says. So because the true parent population mean is known, it is equal to 10, X bar, we do not use X bar, okay? We replace in the sample variance formulation, we replace the sample mean X bar with the true parent population mean, mu. So instead of X bar, we are going to use mu, okay? And we are going to divide the squared deviation, sum of squared deviations with 8 this time, and we get 0.97 this time, okay? Now, my friends, here's the thing, okay? So let's come back here, the previous question. So question 7. So you see these observations, 8 batteries, okay? These are actually real values. I mean, these are not made up. This is not a made up question, okay? Actually, these 8 are actually lifetime of the 8 batteries which are manufactured in a production lot. Okay, so this is a real question actually. It's not a made up question. And the engineer actually designed these batteries to have a lifetime of 10 hours. Okay, for 10 hours. They are going to work for 10 hours consistently. However, obviously, there is some variation in batteries. Okay. So you see, and the standard deviation in the design, the standard deviation is equal to 1. So these values are actually coming from a distribution with expectation 10 and variance 1. I have just collected 8 observations. And in these 8 observations, the sample mean is 9.97, which is very close to 10. And the sample variance is 0.987, which is close to 1. Okay. So as you can see, these values are very successful in guessing the true parent population mean and the true variance. Okay. Practically, this data is coming from a real distribution with expectation, true expectation equal to 10 and true variance equal to 1. Okay. Therefore, even you get a sample size of 8, we can see miracles here. Okay. I mean, imagine what happens to these values if you increase the sample size to 30, 50, for example. And this is typical, actually. I mean, in a production lot of 10,000 batteries that you manufacture, it is possible for you to at least test 30 of them, 30 of these batteries, okay, to make comments on the true distribution of the parent population.